about 62 or 60?
Sir.
Okay. You are able to hear me now? My voice?
Yes, sir.
Okay, good. And only 6 have joined till now? Okay. What did we discuss yesterday? You were there in yesterday's class?
No, sir.
Yes or no?
No, sir.
Why? Are you not regular?
Regular, sir, but I absent yesterday.
Okay, fine. How about 56? Was you there yesterday?
Yes, sir.
Okay, what did we discuss yesterday?
Attenuation, distortion, and noise, sir.
Okay, good.
And we discussed about AC signal.
Okay, then 482, is it there? He or she, where it may be? 482. You were there in yesterday's class?
Sir, I joined a bit late, sir, yesterday, but I was present.
But anyway, what did you, what is the topic we discussed yesterday? Tell me whatever you remember. Whatever it may be, even if you are late, it's okay, doesn't matter. But we discussed, you heard something, right? From that, tell me some points what we discussed. So you don't remember anything?
Four-year analysis, sir.
Okay, good. How about 489? Navya, see there? Did you attend yesterday? Is there or not? Okay, let us take today's class where we continue from where we left yesterday. So, take screenshots of attendance at some point of time, then we can use it. Okay.
Okay, sir.
Yeah. Okay, and then we've been discussing about how to convert these bits into signals or data into signals and send it, right? That's what we've been discussing. And in that process, we discussed channel capacity also. And there are two types of channels broadly: noiseless or which are ideal channels, and noisy channels, which are actually what is available in practice. So in both the cases, we have seen yesterday how to calculate capacity. That means how much data rate those channels can support. For the ideal case, this Nyquist method we use, and for noisy cases, we use a channel method. That's what we are using. Now coming to performance. So one important issue in the networking performance is network, how good it is. Okay, it is quality of service and overall measurement of the network performance in greater detail later. Now let's introduce terms that need for this. Three terms. One is bandwidth, throughput, latency, bandwidth delay product. This probably I think a new term you are hearing now. But other than these three, I think you are already familiar. What is bandwidth, what is throughput, what is latency. Okay. Now, bandwidth, what is bandwidth? We can define the two ways. One is the bandwidth means it is between highest frequency, lowest and lowest frequency that is allowed through a given channel. So first, bandwidth in hertz refers to the range of frequencies in a composite signal or the range of frequencies that a channel can pass through. So this is one way of defining bandwidth. So other way for defining is number of bits per second. That is, second bandwidth is bits per second, refers to the speed of the bit transmission in a channel or link. These are the we define these two ways, and depending on the situation. Now, example, bandwidth of a subscriber line is 4 kHz for voice data. The bandwidth of this line for data transmission can be up to 56 kHz. This is when we were defining in terms of bits per second is this one, 56,000 bits per second, or when you are referring in terms of hertz, 4 kHz. It's one of them. Okay. Similarly, another example. So, so next, similarly, we throughput. We calculate throughput is what, how much data rate it can support. Ideal case, of course, the number of bits received per second in a without errors. So a network with a bandwidth of 10 Mbps can pass only an average of 12,000 frames per minute, with each frame carrying an average of 10,000 bits per second. What is the throughput of this network? How much it can carry? Assume that this is the ideal channel and there is no errors in transmission. Okay, so 12,000 frames you are sending it, right, per minute, and each frame is having 10,000 bits. So that means total number of bits are 10,000 multiplied by 12,000, and that is for minute. So to get per second, divide by 60. That's how we get, and this we can calculate throughput, because this is, we are considering this as a ideal case. So in case of non-ideal, of course, we have to take what are exactly received with respect to how many are really inserted in the channel. Okay. Similarly, the delay. If you take it as delay can have 3-4 components in that. When you are, that means end-to-end delay. When you talk delay, it is actually end-to-end delay. There are, let me see those components. Yeah, what are those components? Propagation delay, transmission delay, queuing delay, processing delay. These are major components, but in between there can be some more switching delay, other things which are very negligible amount. So, but propagation is, this depends on channel characteristics. How much time the channel takes to allow the signal to pass through the channel, okay, from one end to other end. Transmission rate is how much, at what rate we are sending the bits into the channel. Is it this? And queuing, in case it is going through multiple hops, everywhere you have a different unit, whether it's a router, switch, or system, some other node, you need to put in the queue, because as soon as you receive it, you put it in a buffer and process it, and then only send it, right? So similarly, while sending also, you put in output queue, and that's it. There will be two queues, input queue as well as output queue. So the buffer, where the data may wait in queue for some time before it is processed by the system. So that is a queuing delay. Similarly, there can be a processing delay also. So all these together constitute total propagation, total delay. So to make it more clear, I said propagation time is delay is distance of the cable or link divided by propagation speed. Similarly, transmission time is message length divided by bandwidth, the data rate we are sending it, how much time we are taking that. This is how we calculate latency. Now let's go back and see significance of this. What is the propagation time of propagation time if the distance between the 2 points is 12,000 kilometers? Assume the propagation speed is 2.4 10 power 8. Here you have to take it as 10 power 8 meters per second. So, right, how do you calculate? So total, what is the distance of this? 12,000 kilometers multiplied by 1,000. This is to convert into meters, and divide by, because the speed is given in a meters, so divided by 2.4. That you get 50 milliseconds. That means propagation delay, 1 bit once it is inserted to reach the destination, that takes 50 milliseconds. The example shows that a bit can go over the, some distance of 50 meters, 50 milliseconds if there is a direct cable between this thing. So please don't take this Atlantic Ocean, all those things. This is the actual distance is 12,000 kilometers. So it takes 15 milliseconds, because these are main slides were prepared based on the textbook which was written by American. Similarly, another example, what are the propagation time and the transmission time for a 2.5 kilobyte, please remember this message, if the bandwidth of the network is 1 gigabit per second. Assume that the distance between the sender and the receiver is 12,000 kilometers, and the light travels at 2.4 10 power 8 milliseconds per second. We can calculate the propagation and transmission delay as per this one. Propagation time we have calculated earlier, similar to that 50 milliseconds. Transmission rate is, what is it? We said message length. Message length is 2500 multiplied by 8 because it is 2.5 kilobytes, right? So each byte is 8 bits divided by what is the data rate? Data rate, the channel capacity is 1 Gbps, that means 10 power 9. It is 0.02 milliseconds. So here in this case, the transmission time, data which can be inserted in the pipe is much less compared to propagation. Propagation time is dominating. In this next example, if you can see where transmission speed or transmission delay dominates propagation delay. What are the propagation time and the transmission time for 5 million byte message if the bandwidth of the network is 1 Mbps? Assume that the distance between the sender and the receiver is 12,000 kilometers and the light travels at 2.4 10 power 8 meters per second. So same way, propagation time remains 50 milliseconds, whereas transmission time here it is 5 million bytes, right? So multiplied by 8 number of bits divided by 10 power 6 because the channel capacity, the bandwidth is only 10 power 6, so 1 Mbps. So that's why it has become 40 seconds. So 40 seconds is much more compared to 50 milliseconds. So this way, depending on channel length as well as the data rate and channel characteristics. So these propagation and transmission time, one of them may dominate, or sometimes may both become significant. Sometimes may become both are very small. But we have to take all these things into consideration for calculating end-to-end delay. Propagation time, transmission time, queuing delay, and the processing delay. Okay, all of them we have to take into consideration. Then one more term we come across there, right? This is actually bandwidth delay product. It means considering a channel for certain length, how many bits can be inserted or at a time can stay in the pipe. That means what is the bit duration, how much time it is taking for a bit, and what is the length of the channel. So based on that, you can calculate how many bits at a time can stand in the pipe. If you send more than that, if data rate is more than that, so they cannot get into the pipe because once pipe is occupied fully, unless one bit, at least one bit is processed and taken out of this pipe, next bit cannot enter into that. So that means there is no point in sending the data rate more than this. So that consideration we have to take into account. Now let's take this example here. Bandwidth is 1 bit per second. We are sending data 1 bit per second, whereas delay is 5 seconds. Let's say the delay is from here to here 5 seconds. So that means each bit is taking 1 second. So that means how many bits can stay in the pipe? That means in the 5 seconds, 5 bits can stay there. 1, 2, 3, 4, 5. If you try to put more 6 one, there is no space for this. Isn't it? So that's how. Similarly, there is one more example. Yeah, where bandwidth is 4 bps, that means 4 bits per second. Delay is 5 seconds. So 5 seconds. In each second, we are getting that means per second 4 bits can be there. Okay. Sorry. Bandwidth is, sorry. Bandwidth is 4 bits per second. Delay is 5 seconds. 1, 2, 3. Yeah, 1 second. For each second, we are sending 5 bits. Delay is this one. Yeah, it should be 4 here. First 4 bits, second 4 bits, third 4 bits, four bits, next 4 bits. These are 4 bits here. Okay, because we cannot send more than that. So if you send more than that, that means 20 bits at any point of time can stay in the bit. If you, yeah, anything more than that, that's why the answer is correct, but here its representation is something wrong. Okay. So anything more than that, the channel cannot take it, overflows. So that's why this bandwidth and delay product is significant to decide whether you are exceeding the bandwidth delay product while sending the deciding the transmission rate, data rate. Okay, bandwidth delay product defines the number of bits that can fill the link. Anything more than that is overflow only. Now, there is normally we see wavelength in case of analog signals, right? Wavelength. We know how to calculate wavelength. But similarly, in case of binary data, digital data, we have a bit length here. Bit length is what? Propagation speed multiplied by bit duration. Bit duration, say when you are sending 1 bit per second, the bit duration is 1 second, right? So propagation speed depends on the medium. So this product of these two gives bit length. It is analogous, similar to wavelength of given a frequency. Okay. Now the same thing that way you can in another way said that it is bandwidth delay product is similar to cross section of the bandwidth, volume of the bandwidth. Delay is volume. Bandwidth delay product is similar to volume of the pipe. That means length multiplied by cross section of this. That way you can get. Okay. Now this is about signals how to translate. Then let us go to the few questions before we get into next unit. Based on yesterday's and today's discussion, now tell me some questions. Yeah. Let's say a signal is measured at two different points. The power is P1 at the first point and P2 at the second point. If the dB, that means attenuation or gain, is 0, okay, which statement is correct? If attenuation is 0, then which of these statements are correct? Now tell me one of you. Attenuation is 0. Okay. Then which statement is correct? P2 is 0, P2 is equal to P1, P2 is much larger than P1, P2 is much smaller than P1. Which of these statements is correct? Yeah. I think today's strength is very less, only 27. What is this? Yeah. 4A2, unmute and answer this question. 4A2. Are you there? Yeah, whoever is not responding, I have to give answer option for that. 99?
Yes, sir.
Yeah, tell me which of them is correct. Whether answer is right or wrong doesn't matter, but you have to answer it.
Sir, 1 second, sir.
If it is wrong, I will correct, don't worry. But
Sir,
yeah.
option C, sir.
Option?
C, P2 is much larger than P1.
No, you see, dB, the loss attenuation is 0. So that means when it is going from point 1 to point 2, there is no loss at all. That means the power remains same at both the places, right? When there is no loss,
Yes.
dB is 0 here. That means there is no loss at all. No attenuation. That means P2 equal to P1. That's the right answer. Okay.
Okay, sir.
Now let us one more question. Okay. Dash is a type of transmission impairment in which the signal loses strength due to the different propagation speeds of each frequency that makes up the signal. Yeah. Out of these four, which is the right answer? Due to different propagation speeds of each frequency of the compulsory signal, Something happens, please.
Noise.
No.
Attenuation, sir.
Attenuation is
Attenuation.
Attenuation, sir.
attenuation is a loss in the strength, signal strength. Okay, but distortion is change in the shape of the signal. That happens because each composite signal has a multiple frequencies. So when these frequencies are traveling through the medium, each frequency suffers certain amount of delay when it is traveling it. So at the receiving end, due to this difference in the delay of at different frequencies, they reach the destination at different phases. Because of change in the phase, their original shape of the signal will get changed. So this modification of shape of the signal is known as a distortion. Okay, whereas attenuation is only in the amplitude variation in that. Attenuation is amplitude, it changes. The attenuation gets reduced. Whereas this shape of the signal changes. Whereas noise is unwanted signal. Unwanted signal, it may increase the signal strength or reduce the signal strength. That means it affects basically this signal strength, thereby SNR value changes. So that is okay. Now let us go to the today's class, next one. Okay. Yeah, can you see the news slide now?
Yes, sir.
Okay, good. So here we are, I mean, yesterday we, till now we've been discussing about medium characteristics, those things, and attenuation, distortion, that means impairments of medium, all those things. Now let's see some coding schemes. Line coding, this I think you are already familiar in the previous class, but let us go through quickly this thing, because this also is used as a part of this bit transmission in the data communications. So let us review it once again. We see how we can represent the digital data by using digital signals. So conversion involves three techniques: line coding, block coding, and scrambling. So line coding is, and line coding schemes. These things, let us see what these are. So the bits you are getting at physical layer, they'll be using encoder, they convert into different set of bits before converting into signals. Okay, that is encode. Similarly, the receiving end also we do the reverse process, decoding. So when you think about this one, a data element can be represented by a single element, right? Signal element. We are converting data into signal. So here, one data element can be represented by one signal element, or one data element can be represented by two signal elements, or two data elements can be represented by one signal element, or four data segments can be represented by this. That means various combinations are possible. So that means when you are representing one input data element into one signal element, that means there is no change, 1-to-1 ratio here, right? Whereas here, one data element is represented as two signal elements. That means one bit becoming two signals here, really. Similarly here, in this third case, two data elements are represented by one signal element. That means two bits of data is converted into one signal, right? Whereas this one, 4 bits of data is converted into 3 signals. These signals actually defines how much bandwidth is required. Whereas this data element decides what is the bit rate we are getting. Okay, how many bits we are sending it. But those signals are carried by this. These data bits are carried by these signals. So that means this signal defines this one variation in the signal strength. This we call it a baud rate. Okay, whereas data elements are called bit rate. At what rate we are sending the data is called as bit rate, whereas at what rate we are sending the signal is baud rate. This is the difference between bit rate and baud rate. Normally, we keep using these two things interchangeably, but they are not always correct. When only in this case, when the data element, one data element is one signal element, then these two are equal, so we can use any of them. But in all other cases, these two are different values. Okay, so that's why we have to be very, very careful. So, and similarly, this conversion ratio is also, I mean, we can represent as a R equal to 1, R equal to 2, R equal to 1 by 2, R equal to 4 by 3, something like that, right? Yeah, based on that, you can see how many input data is converted into output signals, data signals. Yeah. So, although the actual bandwidth of digital signal is infinite, the effective bandwidth is finite. I mean, channel capacity is that one. Now, this we know how to calculate it, and you can see. 1 bit. When you're transmitting through a channel, this thing, we have to consider, or when you are converting this data elements into signal elements, you have to take some things into consideration. Those things are here. Or when you are selecting a line coding scheme, line coding technique, there are several line coding techniques are there. So while each one has a different characteristic, so but we have to keep some points in view while selecting the appropriate line coding. So there one point is baseline wandering. So what is baseline wandering? Is say a receiver will evaluate the average power of the received signal and use that to determine the value of the income signal. That means running average of the received signal is used for measuring whether just arrived data element is either 0 or 1 or high or low. So if there is, but this one, if incoming signal doesn't vary over a long period, that means there are either zeros continuously or ones continuously, then there is a possibility of drift in the receiver and causes wrong detection of the signal. Maybe one can be detected as 0, 0 can be detected as this. So that type of problem is known as baseline problem. This, so whatever coding technique we follow, that should be capable of overcoming this problem. So that is the meaning of it. Similarly, techniques DC components. DC component. When the voltage level remains constant for long periods of time, there is an increase in the low frequencies of the signal. Okay, most channels or bandpass signal may not support the low frequencies. Okay, when signal is not varying, like long zeros, long ones, anything, so that remains at the same level. And when you convert into frequency using frequency analysis, that produces DC components. And many channels are bandpass signals filters, so they cannot allow this DC component. Another thing is, many channels will have in between transformers. So those transformers also normally cannot pass this DC components from input side to output side. These are the problems. That's why the line coding technique which you select should ensure that there is no DC component in the output. Then only this, you can get the correct detection and the receiving. Next, third is synchronization. So input and output. In case I think in another 10 minutes we are going to come. This one exhaust this time 40 minutes, but please rejoin. Let's take another 10 minutes, then close it. Okay, don't go away. Synchronization. Unless the clock at the sender and the receiver end must have the same bit interval, so there will be always desynchronization. Due to that, we may lose some bits. So example is given. You can see that here. So here we have seen small drift. This is the transmitter side. This is receiver side. Because of this, there is a shift in this. Okay. We'll take another example and see. Because of this, it is detecting extra signal. Okay, during the same time. So suppose you are sending how many bits? 1, 2, 3, 4, 5, 6, 7, 8. 8 bits you have sent here. But how many are detected here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits. So which is wrong, right? So because this is happening because of non-synchronization between transmitting rate and receiver rate. So it should always be synchronized. Okay, now an example also given here. In a digital transmission, the receiver clock is 0.1% faster than the sender clock. How many extra bits per second does the receiver receive if the data rate is 1 kilobits? How many is the data rate is 1 Mbps? There are two cases here. Case 1, 1 kilobits per second. That means 1 kilobyte you have sent it, but at the receiver end, it is 0.1% higher data rate. That means, receiver clock rate. So that means it can receive more than this one at per rate 0.1%. How many is there? That means 0.1 multiplied by this one, 100. There are 1000 bits here. Out of 1000 bits, 1 bit can be received extra here. So that means when you are sending only 1000 bits, it is detecting 1001 bits. So that means definitely there is something wrong. So when you take it at different speed, 1 Mbps, so now you detect much better, much more extra bits. So 1 million bits here multiplied by 0.1%. So it becomes 1,000,000 bits. So 1000 bits extra is issued. So definitely you will not be able to get original data. So there will be error in that. So that's why there should be a synchronization on that. So baseline one thing, the coding scheme should take care of this, and digitally should not produce digital components, and you should be able to self-synchronization. And then self-synchronization, the coding scheme what you produce should be capable of synchronizing the receiver automatically. That is the self-synchronization. And there should be a capability of error detection inside it, and immunity to noise interference, though little amount of noise or interference in between. There should be a coding scheme to be able to correct that and give the correct sequence of bits to the receiver. And the overall complexity of the design should be less, should not be too complex. So these are some of the characteristics of line coding scheme you should consider while selecting it. And what are the different line coding schemes available there? Unipolar, polar, bipolar, multi-level, multi-transient. There are number of things are there. Each one has a different characteristics and merits and demerits. And all these things I think we have already studied in digital communication. So let us not go into much details of these things. Maybe one example we'll see. Skip. So NRZ, unipolar NRZ. So non-return to zero. So that means there is only two levels. Okay, one is represented by one level, another one is zero, another one. Okay, and whereas non-return to zero level and non-return to inverse. So that means when zero is represented as high and one is represented as minus signal. And in this case, second type of scheme. So here you see zero is represented as similar to this one, and 1 is represented to this one. Next, 0 comes. When 0 comes, there will not be any change if you continue same pace. 0, 0. Only there is a 1 density. That's why it is called as inverse. Non-zero, non-return to 0, inverse. So when the next bit is non-zero, then only it inverses the level. So that way each one has a different meaning of these things. So let's not waste time on this because you are familiar with this. And let's go to the block codes. So another variety of codes are block codes, MBNL schemes. A pattern of M data elements is enclosed as a pattern of N signal elements, where 2 power M is less than 2L power N. That means you see number of signal elements are much more than data elements width, so that a subset of this can be represented for this. Subset of these signal elements can be used for representing actual data elements. Okay, that should be condition. Okay, let's see. 0, 0, 0, 1, 1, 0, 1, 1. Each one is represented by different level. Plus 1, plus 3, minus 1, minus 3. Okay. Now this is actual representation here. So here we have used all of them. So that means data, what is it, compared to earlier case, M and L, M and N both are equal here. And there is another one, M 8 bits sequence is replaced with 6 power, sorry, 8 bits and 16 territory levels. Yeah, there are 1, 2, 3, 4, 5, 6. There are 6 patterns here. These every 8-bit sequence is replaced by 6-bit pattern. 8 bits, another pattern. 8 bits, another pattern, like that. Okay, this is another scheme, multi-level scheme, multi-stage transition scheme. So these are some of the summary of this confused, each one characteristic of this. So unipolar, if you in that again, NR is very costly, no self synchronization, long zeros are ones, and DC component also not taken care. Whereas in unipolar, there are 3 varieties are here, and each one has a different characteristic. Similarly, bipolar is one. Multi-level, there are again 3 varieties are there. Multi-line is 1. Each one has a different characteristic. So block code. If you check block code, m number of bits are converted to n number of bits. So these n number of bits are, see, each original data is divided into m different blocks of each m bits. Each m bit block is taken and converted into n bit block, and there again concatenated. Then you will get the bit pattern to be transmitted here. Okay, this is the incoming data, let's say data elements, and this is broken into blocks of m bits. Each m bit block is converted into n bit blocks. So normally here n is larger than m. Okay, so you have more number of bits in each block compared to input block, and when you concatenate all of them, it becomes the sequence to be transmitted. This is the block coding concept. Okay, so same thing, one example is given here. So sender, so we are coding, and then after that we are converting into one of this coding scheme, then transmitting. In the receiving side, you do it in a reverse process. First you extract the original data, from then again using block coding reverse technique, you extract original data elements and hand over to the receiver. Okay, this is an example, and this is also an example. This is another example, and similarly you come across one more term, scrambling. So scrambling is useful in certain cases, where it is really useful. Let's, if you go back and discuss in detail about the previous coding techniques, biphase schemes useful for dedicated short links, but they are not suitable long distances because they use very high bandwidth requirement. In the longer distance communication, getting high bandwidth is very costly. That's why it is not suitable. Similarly, for block coding plus NR chat, if you take, not suitable for long distances because it produces DC component. Now there is another scheme, bipolar AMI.